Hello students, I am Dr. Sunita Tandon from RR College Alwar. Today I am going to deliver lecture number 6 of environmental chemistry of general paper. Today we will study the calculation of global mean temperature. The sun is almost a black radiator with superimposed line spectra. The energy density, that is energy per unit volume per wavelength increment emitted by a black body is given by Planck's equation, and this equation, as you can see in the PDF, is equal to du upon d lambda of lambda, and this is equal to 8 pi e raised to power 8 pi h c into exponential of minus hc upon lambda kt divided by lambda raised to power 5 1 minus exponential hc upon lambda kt. This is equation number 1, where k is 1.88 into 10 raised to power of 23. J, joules per molecule per degree Kelvin, is Boltzmann's constant. H is Planck's constant and is equal to 6.63 into 10 raised to power of minus 34 joules per second. C is the speed of light in vacuum, and it comes out to be 3 into 10 raised to power of 8 meters per second. Lambda is the wavelength of the interest in meters, and T the absolute temperature. Since the sun is emitting radiation mostly from the surface and can be considered as a black body radiator, the total intensity of radiation flux over all wavelength m from a unit area of a black body at any temperature is given by Stephen-Boltzmann law. This law for black body radiation, some students have studied in first year, some in second year, or some will be studying in third year. It comes out to be m is equal to sigma t raised to power 4, where sigma is equal to 5.672 into 10 raised to power of minus 8 watts per meter square per degree, or 34.39 into 10 raised to power of minus 11 joules meter squares per second per degree k raised to power minus 4 is called Stephen-Boltzmann's constant. Radiations from a black body ceases at a temperature of absolute zero. At absolute zero, no radiations are given out by the system. A black body in which is capable of emitting and absorbing all frequencies of radiations, the origin of radiation from such a heated body is given by rapid vibrations of particles. These quantized oscillators emit radiant energy in the form of electromagnetic waves. The emission of radiation spectra is solely dependent on the equilibrium temperature of a black body and independent of its average temperature at any time is close to 290 K, and that of sun is 6000 K. The earth's temperature is close to 290 K, and that of sun is 6000 K. The energy density variation of these two bodies are shown in figure 3. This figure 3, it is energy level diagram or wavelength diagram, and in this case we can see the A is the distribution of energy at 290 degree of earth, A graph is, and B graph is the sun at 6000 degree K as a black body radiator. It is seen that there is a wavelength of maximum emission lambda x maximum which shifts to lower wavelength as temperature increased. It means lambda max for earth will be shifted towards right than sun's lambda maximum will be shifted towards left. The wavelength at which maximum emission of radiation occurs at any temperature is given by Wien's displacement law, and this law states that lambda m into T is equal to 2.898 into 10 to the power of minus 3 meters Kelvin. From the maximum of intensity of any black body, using this relation, average temperature can be calculated. As in sun, lambda maximum is equal to 483 nanometer. Temperature of the sun calculated is close to 6000 K. At 290 K, The entire range of radiations emitted lies in the infrared region, while at 6000 K, 483 nanometer, 90% of solar radiation is invisible, that is 420 to 700 nanometer, and infrared 7000 to 0.3 nanometer. The radiation intensity of the sun varies due to nuclear reactions taking place in it. The solar radiations that actually penetrates to Earth's surface no longer has the spectral distribution of black body at 6000 K. Solar radiations are emitted in all directions from the sun, but the Earth picks up only 2.10⁻⁹ kilowatts of the total solar radiation. At a distance from the sun, this is important, at a distance from the sun equal to average radius of the Earth orbit, the solar energy passing at any surface perpendicular to solar radiation beam is 1372 watts per meter square. This is called as solar constant. You can very well see this in diagram number 4, where Earth is emitting in all direction. Earth is like a black body. Its surface area is 4 pi r square. It is absorbing radiation, and solar radiations with solar constant 1372 watts per meter are given to the Earth at a distance of radius of the Earth, and energy absorbed here is s pi r square. And the radiation which are given out are long wave radiations equal to sigma 4 pi r square T4. Treating Earth as a black body will amount to absorption of all incoming radiations, so that E in is equal to s pi r square. Assuming that Earth is isothermal and energy radiated from the Earth will surface area 4 pi r square is given by Stephen Boltzmann's law, so that equation 2, so that E out is equal to sigma pi r square T4. Under steady state of equilibrium, E in is equal to E out, that is s pi r square is equal to sigma 4 pi r square T4. From this we can calculate T. Pi से pi कट जाएगा, r square से r कट जाएगा, then T comes out to be s upon 4 pi 4 sigma raised to power 1 upon 4, or is equal to 1372 4.4 into 5.67 into 10 to power minus 8 raised to power 1.4, and comes out to be 279 K. This value is remarkably close to the actual global average temperature of 290 degree. From satellite measurements, it has been found that 31% of radiation is immediately reflected by snow or aerosols. This fraction of incoming radiation that is reflected back is known as albedo or alpha. Thus, S into 1 minus alpha pi r square is equal to sigma pi r square Te raised to power 4. From this we can calculate Te. Te comes out to be S 1 minus alpha upon 4 pi raised to power 1 upon 4, or it is, we have to calculate fourth root, and it comes out to be 1372 1 minus 0.7, 30.1% of radiation immediately reflected, absorbed are 0.7. So 1372 1 minus 7.3 0.7 divided by 4 into 5.6 into 10 to the power minus 8 raised to power 1 upon 4. It comes out to be 255 K. The correction that has been applied to account for albedo is calculated at 255 K. The difference in temperature is due to the fact that interaction between atmosphere and radiation emitted from Earth's surface is not considered. That is, it has not included the greenhouse effect. The incoming solar radiations E in per year can be calculated as follows. E in is equal to S, solar constant, 365 days, 24 hours into 60 minutes into 67 into 4 pi r square. This is surface area of the Earth. It comes out to be 1372 365 into 45 into 60 into 60 into 4 into 3.14 into 6371.02 into 1000, and it comes out to be 2.19 10 to the power 22 kilowatts per year. Interaction of radiation with atmosphere traps certain quality of heat so that En is not equal to E out. That is, the greenhouse effect leads to warming up of the Earth. Thank you, students.